cross a bridge today, you probably will not think about it for a single second. And that is exactly the problem, because what is holding you up is not what you think it is, and the gap between what you think a bridge does and what a bridge actually does is the gap between a structure that stands and one that falls. And several of them have fallen with people on them because engineers themselves did not yet understand the physics. The Tacoma Narrows Bridge opened on July 1st, 1940. It was considered a masterpiece of modern engineering, graceful, narrow, elegant. On November 7th, 1940, exactly 4 months and 6 days after opening, it tore itself apart in a 42-mile-per-hour wind and dropped into Puget Sound. Not a hurricane, not an earthquake. A moderate wind, the kind you drive through without slowing down. The bridge did not fail because the wind was too strong. It failed because of something almost nobody had accounted for. And the physics behind why it collapsed is the same physics holding together every bridge you will ever cross in your life, just operating correctly instead of catastrophically. This is not a story about construction. It is a story about force, about how a beam of steel or concrete becomes something that holds 10,000 cars without flexing a millimeter, and under the wrong conditions, something that destroys itself from within. What you think a bridge does, it holds weight. What a bridge actually does is more precise than that. A bridge does not hold weight. It moves weight. It redirects force. Every gram of load that lands on a bridge deck, every car, every truck, every pedestrian, becomes a moving problem the bridge has to solve in real time. The bridge finds a path for that force, from the deck to the beam, from the beam to the cable, from the cable to the tower, from the tower to the ground. Every force gets a route. Every element in that route is either being squeezed or stretched. There is no neutral, only compression and tension. And which of those two a material can handle determines everything that has ever been built. If you enjoy understanding how the world actually works beneath the surface, subscribe. It is the best way to support this work. Drop in the comments what country you are watching from. The research for this script draws on documentation from the National Transportation Safety Board, the American Association of State Highway and Transportation Officials, and verified engineering records. Now back to it. Compression squeezes, tension pulls. These are not complicated ideas, but the gap between understanding them and not understanding them is the gap between knowing why a bridge stands and just assuming it does. Here is the first thing most people never learn. Stone and concrete are nearly useless under tension. Pull on a block of concrete and it cracks almost immediately. Squeeze it and it handles enormous loads without complaint. Steel cables are the exact opposite. You cannot meaningfully compress a cable because it goes slack, but place a cable under tension, under a pure, sustained pull, and it becomes one of the strongest structural elements humans have ever produced. Every bridge design that works is a solution to the same question. How do we route the forces so that stone only gets squeezed, cables only get pulled, and each material only faces what it was built to handle? The arch solved this 2,000 years before steel cables existed. An arch bridge works because its curved shape converts the downward force of gravity and traffic into outward and downward force that travels through the arch material and into the ground at each end. The arch is almost entirely in compression. Every stone pushes against the next stone. Nothing is being pulled apart. This is why Roman aqueducts are still standing, not because of magic. Because stone under compression is extraordinarily durable, and the arch shape keeps stone in compression across its entire length. The Romans understood this geometrically. Before anyone could name the forces involved, they were solving the load path problem without the vocabulary for it, using only shape. The suspension bridge is the arch's opposite, and it works just as precisely. The deck of the Golden Gate Bridge does not float, it hangs. Its weight, and the weight of every vehicle on it, travels upward into vertical hanger cables in pure tension. Those hangers connect to the two main cables, which sweep upward in long curves to the tops of the towers. The main cables carry load and tension to the towers. The towers push downward into their foundations in compression. The cable ends are locked into massive concrete anchorages at each shore, which resist the outward cable pull through their own weight and their bond with bedrock. The Golden Gate's two main cables contain 27,572 individual wire strands combined. The total length of galvanized steel wire across both cables is approximately 80,000 miles, more than 3 times around the circumference of the Earth, all of it in tension, all of it bearing a bridge that handles roughly 10 million vehicle crossings per year. The Brooklyn Bridge did something structurally similar nearly 50 years earlier, and it was unprecedented. When John Roebling designed the Brooklyn Bridge in the 1860s, he specified steel wire cables instead of the iron wire cables every other bridge at the time used. Steel has roughly twice the tensile strength of wrought iron. That single material decision allowed Roebling to build a main span of 1,595 feet, the longest suspension bridge in the world at its opening on May 24, 1883. Each of the 4 main cables is 16 inches in diameter. Each cable contains over 5,000 individual galvanized steel wires. The total wire across all 4 cables, 14,000 miles. Roebling died before construction finished. He was injured in a surveying accident at the bridge site. His son, Washington. Roebling took over and contracted caisson disease from working in the pressurized underwater construction chambers, leaving him partially paralyzed. Washington's wife, Emily Warren Roebling, then effectively managed construction for years, becoming the first person to cross the completed bridge. One structure, 3 people's lifetimes, 1 physics problem, solved with wire. Modern bridge construction goes further than either of those, using a mechanism most people have never heard of despite driving across it every single day. Concrete cannot handle tension. That sounds like it ends concrete's usefulness in bridges. It does not, because engineers found a way to give concrete something it does not naturally have. Pre-stressed concrete does not wait for load to arrive and then try to resist the tension. It absorbs the tension before it ever shows up. Here is what this means in plain terms. Steel cables are threaded through a concrete beam while it is being formed. Those steel strands are then stretched under enormous hydraulic force and locked in place. The concrete is now being continuously squeezed by its own embedded steel, even before a single car drives over it. When a heavy truck later crosses that beam and tries to pull it apart from below, the tension from the truck has to overcome the pre-built compression before any net tension exists. Under normal loads, it never gets there. The concrete never cracks. The bridge carries loads that concrete alone physically cannot carry, because the steel inside is doing the tensile work and the concrete is doing the compressive work, each material handling only what it was built for. This is why modern highway overpasses look almost too thin to be real. That thinness is the physics working correctly. Now the wind. The forces discussed so far, compression, tension, load paths, material behavior, these are the forces engineers had been calculating since the 19th century. What destroyed the Tacoma Narrows Bridge was something different, something that was not being fully accounted for, something that made the bridge itself the engine of its own destruction. The textbook explanation says the Tacoma Narrows Bridge resonated with the wind, like a swing being pushed in perfect rhythm until the oscillations became lethal. That explanation is wrong, and the distinction matters more than it might seem. What actually happened is called aeroelastic flutter. In simple resonance, you need an outside force pushing at exactly the right timing. Remove that timing, the oscillations decay, and the structure survives. Aeroelastic flutter requires none of that. The bridge's own movement changes the aerodynamic forces acting on it, which amplifies the movement further, which changes the forces more. The feedback loop is self-generating. Once started above a critical wind speed, approximately 35 miles per hour for the Tacoma Narrows, the oscillations are negatively damped. There is no restoring force, they can only grow. The reason it happened was the bridge's cross-section. Its sides were solid plate girders, a flat continuous wall of steel. In a sustained wind, that profile behaves like a wing. The deck would twist slightly, which changed the angle of the cross-section relative to the wind, which generated aerodynamic lift in a new direction, which caused it to twist back and then past center, which generated lift again, each cycle slightly larger than the last. On November 7, 1940, the suspender cables began snapping one by one. As each snapped, its load transferred to adjacent cables, which then failed in sequence. The central span fell into Puget Sound in less than an hour from when the flutter reached critical amplitude. A local engineer named Barney Elliott filmed the entire collapse on 16mm color film. The footage still exists. Watch it once, and you understand immediately that the bridge was not breaking. It was oscillating itself to death. After Tacoma Narrows, wind tunnel testing became mandatory for all long-span bridge design. Aerodynamic deck cross-sections became a primary engineering consideration. Open truss designs, which allow wind to pass through rather than load against, became standard where plate girders had been common. Every bridge built after 1940 carries the physics lesson of a structure that solved the wrong problem first. But aerodynamics was not the last lesson bridges had to teach. The most expensive one came 67 years later, on a bridge that had already been officially labeled a problem. On August 1st, 2007, at 6:05 in the evening, the I-35W bridge over the Mississippi River in Minneapolis collapsed. 8 lanes of traffic, 1,907 feet of bridge, approximately 1,000 feet of deck truss fell. The main span dropped 108 feet into 15 feet of water in seconds. 13 people died. 145 were injured. The National Transportation Safety Board investigated. The probable cause was a design error made in the original 1960s drawings. Gusset plates, the flat steel connector plates at structural joints, at a node called U10, had been specified at 0.5 inches thick. They should have been 1 inch thick, half the required thickness. For decades, the bridge stood, because the loads it was carrying stayed within what the undersized plates could tolerate. Then 2 variables changed. Concrete overlays added to the road's surface over the years had increased the permanent dead load on the structure, and on the day of the collapse, 578,000 pounds of construction equipment, sand, and water were staged directly above node U10. The gusset plates yielded. The load path broke at its weakest point. Everything above it fell. The AASHTO LRFD bridge design specifications, the American standard governing bridge design, now requires that every load category carries a quantified probability and that structural resistance is verified with matching statistical rigor. The HL93 loading standard introduced in 1993 accounts for actual modern traffic weight distributions far more precisely than the older standards it replaced. These are not bureaucratic documents. They are the engineering consequences of structures that failed because the standards did not yet exist. The specificity of every clause in those specifications corresponds to a named bridge, a named failure mode, and a documented count of dead. Here is what changes the next time you cross a bridge. Every seam you feel in the road surface is an expansion joint. The bridge is not a single rigid object. It is a series of sections, allowed to move slightly relative to each other, because steel and concrete expand and contract with temperature, and a structure with no room to move would crack itself apart across a single winter. The seams you find mildly irritating are thermal management, operating continuously, whether or not anyone is on the bridge. Every suspension bridge cable sweeping upward in that long curved arc is showing you the physical shape that pure tension under gravity produces. A cable hanging under its own weight follows a specific mathematical curve called a catenary. Add the weight of the deck and traffic and the shape shifts toward a parabola. The engineers calculate both. The curve is not a stylistic choice. It is physics expressing the forces acting on the cable, made visible. Every thin highway overpass you drive under is pre-stressed concrete managing a compressive load it built into itself before you ever drove across it. The thinness is not a risk. It is proof the mechanism is working. The Tay Bridge in Scotland collapsed on December 28, 1879. 75 people died when a passenger train went into the Firth of Tay during a storm. The official inquiry found that the designer, Sir Thomas Bouch, had made no allowance for wind loading whatsoever. Consultants had recommended accounting for 10 to 20 pounds of wind pressure per square foot. The storm that night produced 40 to 50 pounds per square foot. The inquiry's conclusion was direct. The bridge was badly designed, badly built, and badly maintained. Bouch died shortly after the findings were published. Wind load calculations became mandatory in British bridge engineering the following year. One bridge, 75 people, one missing variable in the original calculations. The I-35W bridge had been rated as structurally deficient by the Minnesota Department of Transportation in 2005, 2 years before it fell. Structurally deficient is a defined federal rating, not a vague flag. It means elements in the structure are in poor condition or worse. That rating did not automatically require immediate replacement. It triggered monitoring. The bridge was being monitored while gusset plates at node U10, undersized since the 1960s, were already past their load margin under the new weight placed on them that August afternoon. Every bridge you have ever crossed is the accumulated answer to every failure that preceded it. The arch that still stands after 2,000 years. The suspension cable engineered to exist only in tension. The concrete beam that carries its own compression before your weight ever arrives. The aerodynamic deck cross-section that replaced the plate girder that destroyed itself in a moderate wind in 1940. The gusset plate specification that doubled in thickness after 13 people died in 2007. You are not driving over engineering. You're driving over the exact record of every time engineering was wrong and what it learned. The I-35W bridge had a structurally deficient rating on file for 2 years before it collapsed, and the decision was made to monitor it rather than close it. That decision was made using the information available at the time. The undersized gusset plate had been in the original approved drawings since the 1960s and had never been caught in any subsequent inspection. The bridge was not hiding anything. The problem was in the file the entire time.